All right, let's dive right into this explainer. If you've spent any time writing smart contracts in Solidity, you know that things don't always go exactly according to plan. Sometimes people send you plain ether out of nowhere. Other times they try to call functions in your contract that simply do not exist. Today, we're going to act as a traffic cop to securely route those unexpected payloads. We are demystifying the receive and fallback functions in Solidity. Here's what we'll be covering today. First, handling the unexpected. Then, we'll meet receive and fallback, break down the exact function selection logic, look at some real-world scenarios, and finally, wrap up with some golden rules for developers. Let's kick things off with Section 1, Handling the Unexpected. Picture this. Someone's interacting with a decentralized app, and they accidentally send a payload to your smart contract that it just doesn't understand. What happens? Does the whole thing crash? Do the funds just vanish? Well, when you throw a contract a curveball like that, the Ethereum virtual machine, the EVM, needs a very specific set of routing logic to prevent total chaos. It absolutely has to have a default behavior to fall back on.
Now, it actually wasn't always as clean as it is today. If we look back before 2020, pre-Solidity 0.6.0, contracts relied on just one single fallback function to handle literally everything unexpected. Plain ether transfers, fallback. Non-existent function calls, also fallback. It was, honestly, super messy and led to some pretty notorious security vulnerabilities. So the 0.6.0 update was a total game changer. It introduced a clean split, breaking that one confusing function into the two highly specialized tools we use today.
Which brings us to Section 2, Meet, Receive, and Fallback.
First up, the receive function. This guy is purpose-built for one thing and one thing only: taking in plain ether with absolutely zero data attached. If a transaction hits your contract and the cal data, msg.data, is completely empty, this is the function that lights up. And notice, it doesn't even use the standard function keyword. You just write receive external payable. Clean and simple. On the flip side, we've got the fallback function. Think of this as your ultimate safety net. If a user or maybe another contract makes a call that just doesn't match any existing signature in your code, or if they send a transaction that actually contains data in the payload, the fallback function catches it. It is, quite literally, the fallback plan for your contract's logic.
And this comparison brilliantly highlights how they handle ether differently. Because the receive function's entire reason for existing is to accept plain ETH, it is inherently and always payable. You literally cannot write a receive function without the payable modifier. The fallback function, though, that's optionally payable. By default, it's not going to accept ether. If you want your fallback to catch unknown calls and take their ETH at the same time, you've got to explicitly slap that payable modifier on it.
Let's move on to Section 3, the function selection logic. This is where the rubber meets the road. This decision tree shows exactly how the EVM acts as a step-by-step traffic cop for every single transaction. Here's the flow. Step 1, a call comes in. The EVM checks, does this signature match a normal function like deposit or withdraw? If yes, boom, execute it. Step 2, there's no match. Okay, is the cal data totally empty? And does this contract have a receive function? If yes, route it straight to receive. Step 3, let's say there's no match, but the cal data actually has data in it. Or maybe someone sent plain ETH, but you didn't write a receive function. In both of those scenarios, the EVM routes the call to the fallback function. And finally, step 4, no match, no receive, and no fallback. The EVM just throws its hands up and reverts the transaction entirely. No harm done, but the transaction fails.
Let's see this in action in Section 4, Real-World Scenarios.
So, how does this actually play out in the wild? Let's look at some concrete examples. If Alice sends one ETH directly from her wallet to your contract with no data, boom, that hits the receive function. Now look at poor Bob. Bob makes a typo and tries to call a function named foo, but foo doesn't exist in your code. Because there's data, the signature for foo, it completely bypasses receive and gets caught by fallback. Charlie is a bit chaotic. He sends ETH but also attaches some random, unreadable data payload. Again, because of the data, receive ignores it and it hits fallback. And Dave, he just sends plain ETH, but let's say you didn't even include a receive function in your contract. The EVM will actually look for a payable fallback function to handle Dave's money. If it's there, fallback takes it.
This table perfectly summarizes everything we've talked about side by side. As you can see, receive is all about accepting plain ETH with empty cal data, nothing else. But fallback is incredibly versatile. It's actually the backbone of advanced Solidity patterns, like proxy contracts where you intentionally send unmatched calls so they can be forwarded to a logic contract. Also, take a look at that bottom row. When these functions are triggered via standard send or transfer methods, they are severely restricted by a strict 2,300 gas limit. Which brings us perfectly to our next point.
Section 5. Golden Rules for Developers.
Listen, this is a massive trap for developers, because both the receive and fallback functions might only get that tiny 2300 gas stipend during an ETH transfer. Writing complex, gas-heavy logic inside them is a huge security pitfall. Writing the storage variables, for instance, that costs way more than 2300 gas. If you put complex state changes in there and someone tries to send you Ether using transfer, your contract will instantly throw an out-of-gas error. The transaction will revert, and it could literally break your integrations with other smart contracts. Keep them simple. Usually just emitting an event is all you should be doing here.
If you only take away one thing from this entire explainer, I want you to memorize this exact rule. If someone is just sending ETH, think receive. If someone is making an unknown function call, think fallback. I'll say it again because it's that important. Plain ETH, receive. Unknown call, fallback. This is the ultimate decision rule, and it perfectly summarizes the modern separation of concerns in Solidity.
So I want to leave you with a question to chew on. Knowing exactly how this EVM routing logic works, how are you going to refactor your own smart contracts? Are you safely separating plain Ether deposits from those unknown data calls? And are you keeping your fallback and receive functions gas efficient so they don't break under that tiny 2300 gas stipend? Knowing how the EVM routes every single byte of data gives you the power to build robust, unbreakable code. So don't fall into the messy traps of the past. Thanks for joining me on this explainer, and I'll catch you in the next one.